In the last lecture, we talked about the global problem of tuberculosis. I gave you some statistics on the ongoing morbidity and mortality of this global epidemic. Now I want to talk to you about the tools that we currently have for tuberculosis control. Clearly, whatever it is that we're doing, it's not good enough because it continues to be one of the leading causes of human morbidity and mortality worldwide. The question is this because the tools we have are inadequate, or is it just a matter of implementing more adequately the tools that we do in fact have? It has been opined by many that the tools that we have, if properly administered, could do the job. I personally don't believe that. I think that the tools we have are not adequate to the task, and I hope to convince you of that in this next segment of the lecture. So let's go back to the statistics that I described before in terms of this iceberg of pathogenesis indicated here, where we see that there are large numbers of individuals who die each year of tuberculosis, about 2 million, 16 million or so individuals who are currently ill with the disease, and about 2 billion individuals who are infected and at risk, significant risk of developing tuberculosis in future. That's a huge global burden of disease, obviously, and it begs the question, what about the tools that we currently are using to prevent tuberculosis? I'm sure, as many of you are aware, we do have a vaccine for tuberculosis, the so-called BCG vaccine, which was first introduced in 1921 and is still widely administered. We also have multi-drug therapy for TB that can be effective, and that's been available since the early 1950s, and yet every year about 2 billion people die of this disease, and 2 million people die of this disease, and 16 million people are sick with it. So this begs the question, why aren't these tools doing a better job? Let's start first with the BCG vaccine. Here I've sketched out a brief history of the development of the so-called BCG, or Bacille Calmette-Guérin vaccine for prevention of tuberculosis. The history begins in 1902 when a microbiologist, Edmund Nockar, isolated a virulent strain of Mycobacterium bovis from a tuberculous cow. Bovis is virtually identical to Mycobacterium tuberculosis, the primary cause of tuberculosis in humans. He then gave that strain to a couple of scientists at the Pasteur Institute, Albert Calmette and Camille Guérin, who attenuated it by serial passage in azenic culture between 1908 and 1919, a technique, of course, that was first developed by Louis Pasteur in developing rabies vaccine. In 1921, the BCG vaccine was given for the first time to a human being, a child who was born to a mother who was tuberculous, in a family, in fact, that was tuberculous, and deemed at high risk of developing the disease. The child suffered no adverse consequences and in fact grew to a healthy adulthood without a bout of tuberculosis. From 1921 to the present, BCG has been administered to more than 3 billion individuals worldwide. So on the surface of things, it would seem to be a highly successful, at least a very widely administered vaccine. And in fact, BCG as an immunogen is highly impressive, and it has many characteristics that are ideal for a vaccine against tuberculosis, which I'd like to outline for you here. The first, and this is an important one, is that BCG can be given at the time of birth or at any time thereafter. In fact, it can be given multiple times if that's desirable for boosting purposes. So it's one of the few live attenuated vaccines that is quite safe to give to newborn infants. Why is that important? Well, you want to use a TB vaccine in countries where TB is endemic, obviously, and this overwhelmingly means developing countries, poor countries, where an individual's best chance of seeing a healthcare provider is in fact at birth. If you don't manage to vaccinate the child at birth, you have to wait a few months, you're going to lose a lot of those kids. They will simply not be vaccinated. So that's a very attractive trait. Second, BCG is very safe even when administered to newborns. In fact, the case fatality rate is about 0.19 per million, which is much lower than other live attenuated vaccines such as the smallpox vaccine that have been widely administered. Third, BCG is very inexpensive to produce. It's been said it costs about $0.10 a dose to produce this stuff. Why is this important? Well, as I said, we want to use a vaccine against tuberculosis primarily in developing countries that are poor. So any vaccine that's going to be accessible to individuals in developing countries has to be inexpensive to produce and distribute. Next point is BCG is the most stable live vaccine that's currently in use. It does not require refrigeration in order to maintain its immunogenic properties. Why is that important? Well, again, we want to administer this vaccine to populations living in remote rural areas, that's overwhelmingly where TB occurs, And so it's very important to be able to use the vaccine in environments where the cold chain does not reach. If we had to refrigerate the vaccine, we could not reach nearly as many people. Next, BCG can be administered orally, and it seems to be about equally immunogenic, whether it's given orally or by other routes, for example, percutaneous route. Why is that an advantage? Again, we want to administer this vaccine in developing communities where needles are not always available, and if they are available, they're not always safe, because needles often in developing country scenarios are reused. And that leads to risk of transmission of things like HIV/AIDS, hepatitis C, and so on. BCG is a very immunogenic vaccine in the sense that it elicits both cellular and humoral responses. So you get antibodies and T-cell responses to this vaccine. It's quite potent in that regard. And it elicits immunity at both the systemic and the mucosal level. So as an immunogen, it's a fantastically broad eliciting of immune responses that you get with BCG. Lastly, and this is a huge advantage, BCG seems to confer long-lived memory without the necessity of boosting. So it's very common for individuals who are vaccinated in childhood still to be reactive to the skin test that we use to detect vaccination many decades later, even without boosting. Memory obviously is very important for a vaccine if you want protection that is long-lived. So this is a really formidable list of advantages that BCG has to offer. In fact, it's going to be very tough with any new vaccine to match these advantages. And in fact, BCG, from my perspective, really has only one major drawback, which is that it does not prevent tuberculosis. Admittedly, that's a rather major drawback for a vaccine that's designed specifically for that purpose. Actually, it's a little unfair to BCG to say it does not prevent tuberculosis. It does not consistently prevent tuberculosis. And this has been shown in a large number of clinical trials in which the protective efficacy of the BCG vaccine in preventing adult tuberculosis has been measured. As we can see, looking in different regions, in some trials, such as this one shown here, a case control study, the vaccine efficacy was better than 80%, really quite high. In other trials that are operationally just as good, we see no protection whatsoever. And it does not seem, this pattern of sort of variable responsiveness does not seem to depend on the type of strategy that is used to study the effect of BCG vaccination. And in fact, most compellingly, in kind of what we regard as the gold standard of clinical trials to test a vaccine or a drug or any other new intervention, that is randomized, double-blinded, placebo-controlled trials, we find again this enormous variability from trial to trial in the apparent efficacy of BCG in preventing TB. So in some trials, for example, this one in Haiti, BCG efficacy approached 80%, really quite good. We'd be pretty happy if we had a vaccine that was consistently 80% effective. But in other trials, you can see that the efficacy of BCG was much lower, and in fact, in the largest trial that has yet been completed to date, that was carried out in India many years ago, which involved more than 300,000 individuals enrolled in the trial, the efficacy of the vaccine was nil, no protection whatsoever. And I want to emphasize that operationally, these are all equally good trials that meet the criteria for randomized, double-blinded, placebo-controlled trials. That's about as good as it gets. So we don't understand, there are a number of theories out there, but we truly don't understand at this point why it is that BCG sometimes works and sometimes does not work. There are a number of competing theories. My personal suspicion is that there are probably multiple factors at work here, but one thing is absolutely clear, and that is that we desperately need a vaccine that is more consistently effective than BCG, and I'm not sure how we're going to get there at this point. Now, most of what we know about the immune responses to TB or to BCG vaccination come from studies done in animal models of infection, in particular the mouse model of infection, where we can infect these animals with small numbers of tubercle bacilli by the respiratory route. And I think the kinetics of infection and reinfection that we see in these models provide us with a clue as to why the immune responses that develop against TB are not more effective. So in this schematic, what I have shown is the infection dynamics in a single animal of a typical acute transient pathogen. I've used Listeria as my example because it's a very well-studied acute pathogen, versus Mycobacterium as emblematic of a chronic persistent pathogen. So focusing first on Listeria, what you can see is that after entry into the body, the organism replicates rapidly, reaching a peak and engendering a rapid adaptive immune response to the pathogen. This leads, in most cases, to the total clearance of the pathogen from the animal. And the animal is truly self-cured in the sense that if you were now to immune suppress this animal, you would not see any relapse. So the immunity that develops appears to sterilize the animal completely. That acquired immunity is also quite effective in preventing reinfection with the same pathogen, as shown here. If you take an animal that has self-cured of Listeria infection and attempt to reinfect it, what you see is essentially an abortive infection in which the pathogen never really takes hold and is effectively cleared out. In contrast, when we look at the dynamics of Mycobacterium infection in animal models, what we see is that there is a much longer and period of slow growth in the tissue. So one striking feature of this pathogen is that it grows very slowly in vivo with a doubling time of about 24 hours. So perhaps for this reason, perhaps for other reasons, we really don't understand why. It takes a very long time for the adaptive immune response to rally in TB infection. But when it finally does, this leads to a curtailment of bacterial growth in the lungs, but it does not lead to a diminution of bacterial numbers in the lungs. So what ensues is a kind of stalemate between the pathogen and the host, in which bacterial growth is contained, but in which, in contrast to, say, Listeria, the pathogen is not cleared from the tissue. So there's a failure, if you like, of adaptive immunity to clear the host of infection, which of course leads to a state of latency in humans. That failure of adaptive immunity is also apparent if we look at the kinetics of reinfection of a previously infected animal. And what we see in this case is that the initial kinetics of growth in the tissues of the experienced animal are not altered at all. So the initial growth rate is exactly the same as it would be in a naive, inexperienced animal. Because there are already pre-existing pools, populations of antigen-specific T cells that are capable of recognizing the tubercle bacillus, we see that these infiltrate the lesions about a week or two earlier than they would in naive animals, leading to a curtailment or further growth somewhat earlier and the establishment of a plateau that's about 1 log or so lower than it would be in a naive animal. But there's no elimination of infection in this case either, and there's no prevention of infection. So the kinetics of infection and reinfection in a persistent pathogen like TB are radically different than they are in a transient pathogen like Listeria. And if you think about it, this has enormous implications for vaccine development. The reason is that overwhelmingly the vaccines that we use around the world today are predicated on principles that were laid down by Louis Pasteur in the 19th century. Namely, you take the pathogen of interest, you attenuate it to the point where it is still immunogenic but no longer causes disease, and that's your vaccine. And most of the vaccines that we use currently today, the hepatitis B subunit vaccine being a notable exception, are based on the live attenuated pathogen principle. Now, that's an effective approach if you're talking about a pathogen like Listeria, where the adaptive immune responses that develop in response to natural infection are adequate to prevent reinfection. But clearly, this is not an adequate strategy for pathogens like the tubercle bacillus, where that adaptive immunity is helpless to stop secondary infection. And in recent years, in clinical studies largely in South Africa, it's become very clear that, in fact, reinfection of previously experienced individuals is a major source of tuberculosis disease globally. So to develop a new vaccine that's more effective than BCG, we are somehow going to have to do better than nature. We're going to have to go beyond Louis Pasteur's principles and come up with a vaccine that is more protective than natural infection. The exciting thing is that right now there are efforts underway in many labs around the world to develop such a vaccine, but to some extent I think it's true that we're still flying in the dark. We really don't understand what we want to achieve with a vaccine, either in terms of the immune responses that we elicit or in terms of getting around the defense mechanisms of the pathogen. So this is an enormous area for future research. So we've hit upon the problems of the BCG vaccine as a tool to prevent tuberculosis. Let's talk now about drug therapy as a means of preventing or treating the disease, tuberculosis. So we do have effective therapy for TB, and we have had since 1952. The story of development of anti-TB drugs began with the discovery of streptomycin, a natural product, in the year 1947 by Zellman Waxman, followed rapidly by the development of pyrazinamide and isoniazid, both in 1952, ethambutol in 1958, and most recently rifampin, which was introduced in 1967. So I might point out that since the development of rifampin, the further development of the anti-TB armamentarium has really faltered. We haven't had a new frontline drug for treatment of tuberculosis despite the overwhelming need since rifampin was introduced in the 1960s. And to some extent, I think it's true that the failure, if you like, of the pharmaceutical industry to develop new interventions against TB since introduction of rifampin is a kind of a case of it being a victim of its own success. So it was believed at the time these drugs were developed that a cure had been found that would reverse the tide, so to speak, of global tuberculosis. And this early optimism was reflected, I think, quite nicely in this quote from Zalman Waxman in his optimistically entitled book, The Conquest of Tuberculosis, published in 1964, in which he opined that tuberculosis was on its way to being reduced to a minor ailment of man. He predicted that it would be essentially eliminated as a significant cause of human illness and death in his lifetime. Well, Zalman Waxman has been gone for a long time now, but tuberculosis is still with us. So I think it's appropriate to ask, why did anti-TB chemotherapy fail to live up to its early promise? The proper answer to that question is, of course, multifactorial and complex, but I think there's no doubt that the major problem confronting TB chemotherapy is that it just takes too long to treat this disease. So this slide outlines the so-called short-course chemotherapy regimen that's currently recommended by the Centers for Disease Control for treatment of tuberculosis. It consists of two phases: an induction phase lasting for 2 months, in which 4 or 5 of these drugs are given on a daily basis, followed by a continuation phase lasting from 4 to 7 months, in which these 2 drugs, isoniazid and rifampin, are given intermittently. My point here is that to properly cure tuberculosis requires administration of multiple drugs for a period of 6 to 9 months. It's very difficult, as you will know if you've ever had to take an antibiotic before, to adhere to an antibiotic regimen for a period of even a week or 2. So there's a problem here of patient adherence or compliance. It's simply very difficult to get patients to complete a regimen like this. And the problem becomes more and more acute, if you like, as treatment is extended. That was shown very nicely in a study from Christopher Murray carried out in Botswana in the late 1980s. And in this graph, I've plotted the likelihood that a given patient will default on therapy in percentile terms on the y-axis versus the days that patient is on chemotherapy on the x-axis. And as you can see, it's a constantly rising graph. So the longer a patient is on chemotherapy, the more likely it is that that patient is going to default on chemotherapy. And intuitively, that makes a lot of sense. Once patients begin therapy, they start to feel better almost immediately. Within a month of taking their meds, in most cases, the individual feels that they have been cured. So at that point, it's very difficult to get them to comply with a regimen that is so demanding, that requires them to take multiple drugs every day, many of which have unpleasant side effects, such as gastric upset and so on. So the problem is simply that most patients, in fact, do not complete chemotherapy. In fact, it's in some studies, as many as 90% of all patients on chemotherapy have defaulted on chemotherapy unless that chemotherapy was closely supervised by an attending medical doctor or a nurse or a social worker. The most problematic aspect in some ways of the high rates of default on chemotherapy requiring retreatment and so on is that it has led to the emergence of drug-resistant and even multi-drug-resistant strains of tuberculosis, which are now a threat to global health in every part of the world, as we are hearing these days, even in the United States, with the outbreak of extreme multi-drug-resistant tuberculosis at multiple sites. So here I'm focusing on data taken from the world's 2 most populous countries, China and India, both of which have very high rates of tuberculosis and very high rates of drug resistance. In the case of China and Henan province, where the TB incidence is about 100 per 100,000 population per year, quite a high incidence, they find already that about 1/3 or more of all TB cases that present in clinic are resistant to 1 or more TB drugs, and fully 15% of these cases are multi-drug resistant, meaning that they are resistant to at least isoniazid and rifampin, which are currently our 2 best frontline TB drugs. In India, the rate is rather higher than in China, 400 per 100K in this particular state. The rates of resistance are somewhat lower, but the overall numbers are very similar to China because of the higher rates of disease. So in this case, about 1 out of 4 of all TB cases is already resistant to one or more drugs, and almost 10% of those cases are multi-drug resistant. And this is presenting an enormous challenge in terms of global public health, because in many cases now there are no drugs left for treatment of extreme multi-drug resistant TB, which can be a virtual death sentence for the person who's so afflicted. And of course, this individual can also transmit these resistant strains to individuals in his or her surroundings. So the question arises why it's so difficult to treat tuberculosis. And a model that has been around for some time now, that was first proposed by Denny Mitchison, and which I therefore call the Mitchison Hypothesis, suggests that it's difficult to treat tuberculosis because a population of bacteria in the lungs of a patient is heterogeneous. So he suggested that there are different tissue environments within the human lung, the infected human lung, that lead to different physiologies on the part of the tubercle bacillus. He suggests that in some compartments, the bacteria confront favorable environment where they're able to undergo continuous and rapid growth. And these bacteria are most susceptible to the drugs isoniazid and streptomycin, which are quite effective against rapidly growing bacteria, but poorly effective against slowly growing or non-growing bacteria. He suggested that there are acidic compartments that the bacteria reside in where the drug pyrazinamide, which acts only under acidic conditions, would be most effective. That some bacteria are in compartments where they can undergo only spurts of metabolism, so intermittent metabolism and growth, where only rifampin would be effective against them. And most importantly, he suggested that there are tissue environments where the bacteria are altogether dormant. So these are unfavorable environments for growth, and dormant bacteria are not terribly susceptible to any of the drugs that we currently use to treat tuberculosis. And that is not too surprising if you look at the targets of the drugs that we currently use to treat tuberculosis. It's a variety of different molecular processes that are targeted by these drugs, but they all have one thing in common: cell wall biogenesis, RNA synthesis, protein synthesis, and so on, are all processes that are primarily important for cell growth and division. These processes are much less important for the survival of cells that have exited the cell division cycle and entered into a state of dormancy. So it's quite plausible on first principles that dormancy of a subpopulation of bacteria may explain the recalcitrance of TB to therapy. And remarkably, there's actually some clinical evidence that would support this hypothesis. This comes from a study that was quite remarkable, published in the 1956 by Vendivere and colleagues, in which they sampled lung lesions taken from patients who had been on chemotherapy, in many cases for a year or more, and they cultured the bacteria out of lesions within the lungs of these patients. Now, they classified these lesions into two categories according to whether they were closed and appeared to be dormant, that is, these were lesions that were more or less inactive but persistent, or open and active, where the bacteria were clearly undergoing luxuriant growth. From the active lesion, they found that overwhelmingly the bacteria they isolated from these lesions were resistant to the drugs that the patient was being treated with, which explains why the bacteria were not cleared. They were simply resistant mutants. And the colonies of these bacteria appeared in what is considered a normal time course for the tubercle bacillus, which is 1 to 2 months. As I indicated before, it's a very slow-growing bacterium. So 1 to 2 months is about what you expect for actively metabolizing bacteria to form a colony. In contrast, when they cultured the bacteria from these closed lesions, they found that in most cases they were still drug sensitive, even though they were coming from individuals who were undergoing active chemotherapy with drugs that these bacteria were susceptible to, and that the outgrowth of these bacteria was delayed quite substantially. These observations suggested that the bacteria in these lesions might have been in a state of dormancy which protected them from the killing action of these drugs. And if it's true, as Mitchison proposed, that these dormant bacteria are always present as a subpopulation, even in individuals with active tuberculosis, this could explain why it's so difficult to treat this disease. And it would suggest that for the development of new and more effective drugs against TB, we should perhaps be focusing on targeting processes that are required for survival of non-replicating cells rather than active cell growth and division as we have in the past. A completely different set of molecular targets. Now, given the obvious need that I've described to you, you might think that tuberculosis is a major priority for the pharmaceutical industry and for governments even in the rich world. because the human need is so overwhelming and so obvious. That's a reasonable conjecture, but you'd be dead wrong if you thought that. And the reason for that is illustrated graphically here, where I've plotted data from a recent human development report from the United Nations. On the y-axis, I've plotted TB incidence per 100,000 population. On the x-axis, the Human Development Index ranking of countries according to the United Nations. So each dot in this graph represents one country. And Human Development Index indicates human development in terms of income, health, and so on. So a low number, according to the Human Development Index, is a good thing, and a high number is a bad thing. And I have not drawn a regression curve through the data here because it's really not necessary. As you can see, the correlation is quite clear. Where human development is low, as out here, the rate of tuberculosis in the population is extremely high. Where human development is high, the rate of tuberculosis is low. Here's the United States, represented by the blue dot right here. So there's a very clear and striking relationship between tuberculosis and poverty. And in fact, it's the case that 99% of TB cases, people who are ill with TB, occur in developing countries, and 99% of TB deaths occur in developing countries. So this is overwhelmingly a disease of the poor. And for this reason, pharmaceutical industries and governments of rich nations have traditionally not seen a lot of incentive to invest in development of new interventions and strategies to prevent and to treat tuberculosis. I'm happy to say that this is beginning to change. I think in developing countries we are waking up to the reality that we live in a global community that is shrinking all the time with advances in transportation and increased migration from country to country, such that health in developing nations, in fact, does develop our own personal well-being and health. And we are seeing, largely led by non-governmental organizations such as the Bill and Melinda Gates Foundation, a renewed interest in confronting global inequities and inequalities in health, tuberculosis being one of the most striking examples. So I'm quite hopeful for the future that there will be increased investment in these areas and increased attention paid to the development of new vaccines and drugs against problems like tuberculosis. As I've tried to indicate, however, the scientific challenges for developing new interventions against TB are really quite formidable. And this, I think, is where those of us who work in academia have an important part to play, precisely because there is not as much investment in these areas on the part of the pharmaceutical industry as you would see in a field like, say, cancer, cardiovascular disease, and so on. Those of us who work in academia and who are free from the constraints of profit motives and the like have a special role to play. We can drive a lot of the basic research and development in areas like target development, antigen identification, and so on, that the pharmaceutical industry then can use, if we can hand them sort of a ready-made package of information for the development of new interventions. So I predict that what we're going to see in the coming years is a growing number of public-private partnerships where the basic research and development will be done in academia, and the actual product development and clinical trials will be done in the pharmaceutical industry. An alliance between the public and private sectors in service of global health in the world's most underserved populations.